Okay, so welcome back to the second part of the pre-tutorial, pre-conference tutorial. And I'm trying to start where Raghu has left off and talk about double holographic settings or double holography. So I will call this in short. Okay, so before we get started, or before we sort of talk about double holography, let's maybe just review what Raghu has talked about, and let me just emphasize sort of the main few messages that I hope most of you took away from the talk. Okay, so remember the setting and the questions we asked were as follows. We're considering a quantum mechanical system that could be an SYK model, and is symbolized here by this small green box, which is dual to some gravitational space-time, which on the right here is shown as this green triangle. Now, on the right here, time runs upwards, and on the left, I've suppressed time. So this really should be thought of as a time slice. And then this quantum mechanical system is coupled to a quantum wire on which a CFT lives. And this quantum wire should be thought of as a time slice sort of this pinkish region, where a CFT lives, but it ends at some point where here it gets coupled to this quantum mechanical system. Okay, now we said we would choose our holographic system in a nice and appropriate way, such that on this space-time here, which splits into this non-gravitational part in pink and the gravitational part in green, such as on this background, we have a CFT living, and the CFT can freely cross between those two regions. The questions we wanted to ask were either, what's the entanglement entropy of a subsystem of my quantum mechanical system here on the left? Or perhaps, how much of my space-time, the gravitational part, is actually encoded in some subsystem of my quantum mechanical system on the left. And the way this question is answered is that the parts of my non-gravitational space-time sort of match nicely onto my pink region in space. So if I consider some interval in my quantum mechanical system plus the quantum wire here, then the interval has a right boundary, which maps to some right boundary in the non-gravitational region. So I'm considering this red interval here. And then the left boundary is determined dynamically by using the quantum extremal surface prescription. So I'm looking in JT gravity for a particular saddle point of my dilaton, and this marks the end of my interval. Now, surprisingly, what Raghu found, or what we've seen, is that if I consider all of my holographic system, all of my SYK, or whatever I want to have here, together with a bit of my bath, perhaps, I will not, or this region here will not correspond to the full gravitational region and a bit of my bath, but it will correspond to a bit of my bath and then just some portion of my gravitational region. Now that's surprising, because usually we might have thought, just by thinking about standard ADS CFT, really that this little quantum mechanical region here should be dual to the full gravitational spacetime. Now we see it's not, and then we might ask the question, so what about this other region to the left of my quantum extremal surface in the gravitational spacetime? Where is this encoded? And Raghu sort of gave a very quick argument, which we'll hopefully also discuss a bit later, namely that we should think about the system as containing complements and complements. So what I mean by this is that the complement of this red region in the upper picture is the orange region in the lower picture, and that contains the missing piece of our gravitational spacetime, and then also a large portion of my non-gravitational part of the spacetime. And so this should be dual to the complement in my quantum mechanical picture here, which is just part of my quantum wire. And so this region does not contain anything of my little quantum mechanical SYK system here, but still somehow describes this region in the gravitational part of my spacetime, which seems completely disconnected from the subsystem I would naturally associate with my quantum wire. And so this small region here is called an island. So I hope everybody sort of remembers these key facts. And with that, we can go on. Okay, so right. Okay, so hopefully that the last sort of 90 minutes have convinced you that these non-trivial quantum extremal surfaces are curious and they somehow seem important, at least to some degree, for understanding quantum gravity and what goes on in black hole evaporation, right? Probably everybody here has heard that they now allow us to actually calculate some sort of page curve. But much of the work on this has been done in 2D. This is explicitly not the paper by Geoff Pennington, which is where he argued in 4 dimensions, I believe. But the full first tutorial today was in 2D and many other things. Now, the problem with 2D is, of course, that it's 2-dimensional and 4-dimensional. And gravity in 2D is qualitatively also quite different to higher dimensions, and starts with the fact that we have a dilaton and no gravitons, but then goes on to a bit more subtle issues, which I'm not going to discuss here. But let me just say that we can UV complete 2-dimensional gravity using systems which are intrinsically random. And we don't necessarily expect this to be true for a higher dimensional system. So for example, if I just do ADS CFT with a 4-dimensional CFT, like n equals to 4 super Yang mills, then I generally assume this system has just some fixed Hamiltonian, some fixed couplings. Everything set, there's no sort of randomness to it. So my plans for the next hour-ish, 50 minutes, is to show you or to look at the problem of islands in higher dimensions, and sort of along the line, just introduce some terminology and concepts which hopefully will be helpful in understanding islands and also be helpful in the conference. And the first part of the terminology is what's known as the island formula. So you might ask, well, what if I don't want to sort of like do all this shenanigans from like having my quantum mechanical system coupled to a wire and then do some duality and then take some complement and so on and so forth. But I just give you some gravitational system or like a system which consists of a gravitational and a non-gravitational space-time, and I ask you, okay, there's some region A. Does this region actually contain information about some island? Like, what if, like, how do you answer this question? And the answer is there's a new prescription, or new proposed prescription for how to compute the true quantum gravitational, and I'll explain in the next few minutes also what I exactly mean by this, entropy of this region A. And instead of just sort of taking the density matrix in some semi-classical approximation and calculating its von Neumann entropy, what you should do is you should consider all possible disconnected regions in this gravitational space-time. Then you compute the entropy of A union this region I, and you pay a penalty for having this region. And the penalty is the area of the boundary of this island, so which in 2 dimensions was the value of a dilaton, over 4G Newton. And then you extremize over all choices, over all possible choices of islands. And one naive choice you can make is just the choice of no island at all. And then the extremization is sort of trivially done. You just find the semi-classical entropy of A. But in some cases, you will find that there are some additional extrema. And if you have several such extrema, you have to take the extremum which gives you the minimal value of your total entropy of this functional. Okay, so this is the new rule that was introduced in a paper by these people. By the way, I'm going to be very, like, I'm not going to be giving you a lot of references, really only sort of occasionally, because I think that's a tutorial session. And in that context, it might be okay. It really, everything I say here was developed by a lot of people, many of which are talking at the conference next week. So this is where you find all the information. Okay, in any case, if you see this island formula, you might be confused by a lot of things. First of all, now I've introduced some SQG and some SC, where SC stands for semi-classical. What are those things? It's kind of weird. I want to compute an entropy, and I'm instructed to compute an entropy and add some area and consider some islands, and then I minimize over stuff. So what's up with this? What do these quantities really mean? They obviously can't be the same. Then second, very surely, like, why would that formula actually be correct? And then maybe lastly, we've seen that something like this seems to work out in 2 dimensions, but what about higher dimensions? Is there sort of any way I can convince myself that that's true? And what I'm planning on doing now is to sort of like clarify these puzzles, not really prove anything, but give you an intuition using doubly holographic models. Just quickly, why are they great? The island formula I introduced on the last slide really, in this context, follows from very basic standard facts about ADS-CFT, namely the RT formula without any quantum correction or anything, perhaps entanglement wedge reconstruction, or very basic features of the holographic dictionary. And then, of course, there's some sort of like secondary reasons. I'm hopeful to show that actually these doubly holographic models also will make an appearance in the workshop, perhaps in the context of cosmology, but we'll see. I don't really know what everybody's going to talk about. And also, and I might show you, if we have enough time, an example of this, these allow you to push calculations in higher dimensions analytically very, very far. So you can actually sort of show more or less analytically that you will have a phase transition if you have a black hole which evaporates or is in contact with a bath in higher dimensions. Okay, before we sort of start all of this, let me just point out that the route Raghu and I have been taking can be sort of like complemented by taking a different route of discussing quantum extremal islands, namely by considering replica wormholes. So these are a particular saddle point in the Euclidean path integral. And there's this wonderful review that appeared in June on the archive. It's super accessible, and it, I think, very nicely sort of introduces a different perspective, which we don't really talk about here. Okay, are there any questions at this point about the island formula or anything else I've said? Great. So if not, then let's maybe start talking about double holography or doubly holographic setups. So what we've seen so far looks a bit like the left of this picture here, right? We have CFT, which I've really called now a boundary CFT because it ends somewhere. And at the point where my space-time on which I've defined my CFT, so think this goes off to infinity. And I've introduced this one-dimensional defect, and I say, okay, that's some holographic system, which itself is dual to JT gravity, plus a copy of the same CFT on the background. Okay, so if I sort of then perform holography on this defect, I'll get something like this, right? I have my CFT on some rigid space-time, which was just Minkowski space in the previous example. And then I have some dynamical theory of gravity. But now what I can do is, let's assume that my two-dimensional CFT actually is holographic itself. And so what we would expect then is that near this boundary, I should just be able to do a standard ADS-CFT. So I get some asymptotically ADS space-time in one higher dimension. Now, near the brain, it's sort of like unclear this is what happens, but we can make a few guesses. Namely, we expect that our space-time gets cut off at some point, like the CFT here gets cut off by this defect. And so this is what I've indicated here by the Planck brane. And you might also guess that this Planck brane isn't really an asymptotically ADS space, but sits at some finite distance, and this has to have some dynamics, which fits nicely with this picture of sort of this region here, which I've drawn at roughly the same location as this Planck brane, having or containing JT gravity or a dynamical theory of gravity. Okay, so why would we do this actually? Why do we introduce yet another layer in our description? The reason is, and Raghu already mentioned this, that computing entanglement entropies is generally real hard. And in particular, in higher dimensions is real hard. However, if our theory is holographic, we can cheat a bit. And instead of calculating this hard entropy, or doing this hard calculation of entropy in our CFT, say in higher dimensions, we can use the RT formula. So the whole calculation geometrizes, and on the right-hand side, I have an area which I have to compute here, and then I have an area in higher dimensions which I have to compute here, right? So just very roughly speaking, right, I consider some region A here, and in order to compute its entropy, I have to compute the area of an RT surface, which maybe looks like so. And then just a very quick reminder of the RT formula, just so we get this out of the way, right? The question is, given some subregion A and the reduced density matrix on this region, what is its von Neumann entropy? And the answer is you take a surface A, which is homologous, so A tilde, I've called it, I think Raghu called A star, which is homologous to A. And so, and this surface A tilde is supposed to extremize the generalized entropy functional, which consists of the area, and then there's probably corrections if you have not just Einstein gravity. And there's a contribution coming from the quantum fields inside this region. Now, for our purposes, we can actually ignore this contribution in the following. Yeah, essentially because this here will just be small in our case. Again, there's this thing which I've already mentioned for the Allen formula. There might be multiple different candidate RT surfaces, so areas which extremize the generalized entropy or just the entropy. And if there are many, we just pick the smallest one. And that will come in very important later. And then secondly, one thing which is also going to be important later, that of course the entropy has, from the quantum field theory point of view, UV divergences, which come from entanglement of high energy modes across this surface between A and its complement. And from the bulk point of view, this here is a representation of an infrared divergence. So remember ADS, the asymptotic boundary is infinitely far away. So if I calculate the area of the surface, I'll get a very large contribution sort of from this region here, which in fact will be infinite. And so these UV divergences I have to regulate somehow. All right, so just to sort of wrap this overall idea up and introduce some more notation, right? What we're looking for now is in higher dimensions for a system which does not only have two, as we used to in standard holography, but three different, maybe equivalent, but as we'll see, not really equivalent descriptions. One is sort of a purely quantum mechanical, quantum field theoretical, no gravity perspective or formulation, which I will call the boundary perspective for reasons that will become obvious in a second. And then the third one is what I call the bulk perspective, which is just gravity in some higher dimensional spacetime. But now, so this is what we're sort of used to from standard ADS CFT. But now there's this third description here, which is sort of hybrid. There's a part of my spacetime which is rigid, and a part which has dynamical gravity living on it. And then there's a theory living on both of these parts of my system, and they can cross between those two regions freely. And so I will call this here the brane perspective, and I will also often refer to this rigid region as a bath. All right, any questions so far? If not, then let's go on and let's see how we can construct such models in higher dimensions. So luckily, essentially, the work for this was already done around 99 and 2000s by Randall Sundrum and Karch and Randall. And sort of we've just taken this and applied this to the more recent developments in some paper, and there's also some work by people from UBC and some work by people in Princeton. But yeah, so I'm sort of going to go along the lines outlined in a few papers we've written. And I'm going to try to explain these higher dimensional brain world models by appealing to the standard ADS CFT dictionary and just like kind of going along in parallel. So remember, ADS CFT, the standard dictionary just tells me I have CFT on a d-1 sphere times time, and I've just suppressed time here, and that's dual to ADS d+1. Now, what I can imagine doing is I just add a defect along a great circle to my CFT. So what is the dual description now in terms of in my ADS space? Well, one way I can model this, and I will model this, is I introduce also a defect, which is, in my case, just a brain into the interior of ADS. And I'll introduce it in such a way that at the location where this brain intersects the boundary, I will find my defect in the CFT. So this defect should be codimension 1, as you can see in all those pictures. Now, from the ADS point of view, this brain might have like a bunch of couplings and a theory living on it, perhaps, but we'll just focus on a very simple case where this brain is characterized by its tension, so it's coupling to gravity. And I can tune this tension parameter and therefore control the back reaction of my brain. So if my tension is 0, there's just a probe brain sitting in ADS. But if I increase my tension, then the back reaction will create a bunch of extra volume around here. Now, this extra volume will take a very particularly nice form. Namely, I can imagine or I can treat the system as the following. If I just consider the geometry to the left of my brain, this is the same as considering sort of like a complete copy of ADS, which I've just cut off on some slice, let's say somewhat near the boundary. And so this here now should be thought of as, say, vacuum ADS, and here this would be some warped geometry, and you can just map between them. And the same happens on the right. So the right-hand side, if I choose my tension sufficiently large, the right-hand side of my brain will again almost look like a full copy of ADS, just that at some point it's cut off by the brain. And of course, I only have one brain here, so really I need to identify those two things, which is indicated by these orange arrows here across the brain. Sorry, not across the brain, but I should identify points on the brain. OK. Now, just in case the question comes up, you might want to ask, so if I tune this tension here, if I increase the tension, what does that mean in terms of my CFT defect? And so what we want to do is we want to imagine that there is a codimension 1 CFT living on this defect, and the number of degrees of freedom of this additional codimension 1 CFT more or less corresponds to the tension. So if I have a CFT here with a large number of degrees of freedom, this tension is really big, and I create a lot of extra space here. And if the number of degrees of freedom in the CFT is small, then tension will be small, and this brain here will sort of sit more towards the center, and so I've created less geometry.
I have a question.
Yeah.
So it looks like from these diagrams that you've essentially just anchored a brain to the defect on the CFT.
Yeah.
And just from the picture, is it clear that the brain won't have its own dynamics, like wiggle around in the bulk while still being anchored?
Oh, it will generally, right? This is like the brain is like some dynamical object. What I will focus on here, though, is just sort of just the situation where this here is all vacuum ADS. And so, of course, the brain will have some dynamics, but I'm just looking at the vacuum state of my theory.
Okay, thank you.
All right.
And can I ask?
Yeah.
Is it not dangerous? How do I understand that you have something which is meant to be like you have the bulk and then you have the thing which is dual to it and is meant to be a copy of it? Are you somehow interacting a quantum state with its copy?
Okay. Let me just answer the question. I think I understood, and then if that's not your question, maybe repeat this. So here. Like, this is not a duality. This is just an equality. I just go to a different coordinate system, really, between those two descriptions here. What my duality is just CFT is dual to ADS, and here CFT with a defect is dual to ADS with a defect. And so this is sort of just up until now very standard ADS CFT. Now, did that answer your question at all?
I guess it's about this brain which can interact with both the bulk, if I understand, is interacting both with the bulk and the boundary.
Oh,
and whether that's not dangerous that it's somehow interacting with essentially.
No, it does not. It doesn't interact with both, right? It's just like in the same way as my CFT has a dual description as an ADS space, my CFT defect will have a dual description in terms of this brain.
Okay. Thanks.
Okay.
I just have another question.
Yeah.
So what usually when you move you have this cutoff surface, and that somehow corresponds to some kind of coarse graining of the UV degrees of freedom. So is the defect somehow related to that?
We will see that exactly this becomes very important for these doubly holographic scenarios. But right now, I just want to point out, right, that the true CFT boundary is this black line, which goes around here and then continues around here. Okay, and so the brain really sits in the middle of the bulk. But we'll come to the point that this almost looks like full ADS with just a cutoff, and whether or not there's some coarse graining going on.
Okay.
Okay. So yeah, let me just go over this real quick. So you might say, but why would I believe you? You're just saying there's some brains. I'm obviously not going to prove this, and also I won't be able to prove this because this is a model. And if you try to construct such solutions in actual, like say supergravity, it's a bit more involved. But just to check that we didn't do like a very stupid mistake, right? We can see again if the symmetry groups of our two descriptions agree. And remember, in standard ADS CFT, the conformal group in D dimensions is SOD, 2, which happens to coincide with the isometry group of ADS-D plus 1. And now if I choose a particularly nice defect in my CFT, I'll find a symmetry group of SOD minus 1, 2. And so how do I see this in the ADS? Well, what I can do is I can slice my ADS space, my ADS-D plus 1, by these blue slices here. And each blue slice is actually has an induced metric of ADS-D. So I slice ADS-D plus 1 in terms of lower dimensional ADS leaves. And then there's this orthogonal coordinate theta. And so as long as I place a brain at some constant theta, which I've done here, I'm definitely left with the isometry group of these ADS leaves here, which also is SOD minus 1, 2. So there's again a nice match. Okay, so what I've shown you so far, again, is just the standard bulk and boundary perspectives of standard ADS. I know the question is, okay, well, we were looking for a system with 3 different perspectives. How do we get this, what I call the brain perspective, this hybrid thing where I have some space-time where I don't have gravity coupled to something where I do have gravity and a theory which can sort of freely move between those 2 regions? Now, again, usual ADS, right? It's ADS is dual to a CFT on the boundary, and here, and I think Krishan was that sort of pointed that out already, that, well, in a way, it just seems like ADS is cutting off, the brain is cutting off my ADS close to the boundary. And so if I'm just being very vague and wave my hands, you might just take the system and try to do standard ADS CFT and just say, okay, why, can't I maybe replace my bulk system here where my brain almost sits at the boundary by some other system where I have my CFT on one part, and then something which lives at the brain which will almost look like my CFT. Another way of sort of doing this is simply saying what you want to do is you want to integrate out the bulk, but you don't want to integrate out the bulk from one boundary all the way to the other boundary, but from one boundary to the brain, then you skip the brain, and then you integrate out the rest of the bulk. Okay, so you can do this, and the resulting theory will have 2 key features. And these are the two features we were actually after. So one is that on the brain, I'm just dropping sort of like the second copy of my system here. On the brain, I will have a copy of the CFT, which I have in my bath region, which will happen to have a cutoff. And I'm going to explain to you why that is in a moment. And then secondly, apart from the fact that there's a CFT now living on this green part of my boundary, I will have also dynamical gravity living on this brain. So this here will essentially be a copy of my CFT coupled to gravity, very similar to what we saw in the two-dimensional model. OK, so to see why that is, we have to use our ADS CFT toolbox a bit. And so let me try to make this a bit more intuitive. So usually ADS CFT can be formulated as an equality between partition functions. And if we evaluate the partition function in our gravitational system, then we find it's infinite. So we got to regulate it somehow. And if we introduce some regulator, some cutoff near the boundary, we'll find that there's two terms. One term, which is just our CFT effective action coupled to gravity for a CFT with a cutoff. And then there's this other part, which looks like a bunch of terms constructed from the metric induced on my cutoff surface. And the leading order terms, if I go very close to the boundary, are just the Einstein-Hilbert action with an induced metric, which depends on my cutoff, and with a cosmological constant that depends on my cutoff. Now, if I was integrating up to the true boundary, like here, then what happens is, as I send my cutoff to 0, this gravity term becomes very big, and I have to subtract it to get a finite result. Now, if I look at the situation close to my brain, of course, my brain sits very close to the boundary, so the gravitational part will still be very big and will be there, but I'm not adding any counter terms to remove it. So really, the situation sort of around this brain, or integrating up to this brain, will give me some Einstein-Hilbert action, which comes from these terms I would usually subtract, plus a CFT with a cutoff. Now, I never sent the brain all the way to the boundary, so these cutoffs are all going to be finite. So I have something manifestly finite. But in particular, I will have a CFT which has some sort of built-in UV cutoff. And I shouldn't really treat this as a CFT with the fixed point in the UV. And then there's a second aspect to this, namely to the fact that I have gravity on the brain. So I already have my Einstein-Hilbert action, and then there's some subleading higher curvature corrections here. And in order to suppress them, I have to push my brain very far to the boundary. But you might ask, OK, but I expect my theory to have gravitons, so where did they come from? And this is sort of the very special thing that Prandtl and Sundrum found, namely that in these settings, there will be a bulk graviton mode, which is strongly localized around my brain. So I can effectively treat it as just being localized to my brain. And this will play the role of the graviton in this green theory. OK, again, to sort of sum this up and add a bit more layers to it, right? We have this boundary perspective. So the boundary perspective was just some CFT coupled to a defect. Here we had a BCFT coupled to a defect. Now, if you like this picture better, just take a Z2 quotient across the defect here and identify points here with points here, and then it looks very similar. I've just sort of opted for this description here because I think it's conceptually a bit more clear what's happening. Then we have this brain perspective where we have a bath region, which is my sort of true CFT boundary, and then a gravitational region, this green region here, which is some sort of has an approximate CFT living on it and has some higher curvature gravity on it, where all the higher curvature terms are very much suppressed. So it's essentially Einstein gravity coupled to a CFT, but really only it's an approximation. And then we have this bulk perspective where we have a higher dimensional gravitational description, and we use it only as a tool to compute entanglement entropies. OK, I think that's a good place to maybe stop for questions, if there are any.
Yeah, I have a question.
Yeah.
In this brain perspective, I don't really understand how is it possible to have a gravity theory coupled to this bath theory, because like gravitons leaking in the bath place and making gravity dynamic also in there. I don't understand how is this realized.
Oh, I see. Well, maybe the clearest answer is that remember that on these, so the brain here was just a particular slice. When I had my slicing coordinates, I would foliate my ADS bulk with ADS leaves, and this brain just lives on one of these leaves. So gravitons don't leak out because really the theory on this, or the space-time in this green region is asymptotic, it's just asymptotically ADS. And so in the same way that in standard ADS CFT, sort of gravity becomes weaker and weaker as you go to the boundary, the same thing happens here.
Okay, thank you.
Okay, so if there are no more questions, then let's finally get to the point. Why are we considering these models, right? Remember, islands appeared in fairly simple questions like, oh, if I'm like in my boundary theory, what's the entanglement entropy of, say, these two caps here, which I colored in red? Now, we can go to the bulk perspective again. There's it's just standard ADS CFT, nothing fancy involved yet. And we know how to answer the question. We're looking for RT surfaces. And in that case, there are two possible RT surfaces. One set of RT surfaces just connects sort of or caps off the caps, if you will. And the other RT surface connects through the brain. And so the question is sort of, how do these situations look like now in the brain picture? Because remember, the brain picture was the one where we saw islands appearing also in the two-dimensional case. And as you might already have guessed, the answer is that whenever my RT surface crosses the brain, then the intersection of my brain with my RT surface will be the boundary of an island in my brain perspective. Okay, how do we see this? Well, I've already mentioned that RT surfaces diverge, or the area of RT surfaces diverge near the boundary. And on this side, so where we have our CFT living on a rigid spacetime, we understand this in terms of UV divergences of our CFT. We have modes which are just decoupled across this entangling surface here, so the boundary of region A. But now again, remember, we have our brain chosen very close to the sort of like a would-be boundary of ADS. And so the RT surface also gets a large contribution from this region close to the brain. And it turns out, if you calculate what this contribution is, it will take the form of the area of the boundary of your island over 4, what I've called G effective here. And G effective is just the gravitational coupling in my brain theory. And so really, I can sort of split the area of my RT surface, which is supposed to give me the entropy of this region A, into 3 pieces. One UV divergent part, which just comes from here, which I understand in terms of my quantum field theory here. One what I call UV finite part, which is a large contribution, which comes from close to my brain. And this just takes looks like an area contribution, proportional to the area of the boundary of my island, and then sort of details about how my RT surface behaves deeper in the bulk, in the IR. And this will just give me the entanglement entropy between modes in my island region and in A. So what this means, that just taking the standard RT prescription and interpreting this from the brain point of view, what I really want to extremize is not the area of the bulk RT surface, but now the area of sort of, well, the area of the boundary of my island over 4G Newton plus the entropy between A and I. This is extremized, and the extremization is exactly the same extremization, or follows from the same extremization you would do in the bulk, where you just extremize your RT surface. And then again, if you have multiple options, you minimize over all your choices. Now, what this explains to you very nicely is what is meant by this SC or semi-classical and SQG, right? So this entropy I'm calculating on the left is really the entropy, let me just go back, in my boundary prescription here, which I can sort of like treat as a fundamental description of my system, whereas the entropy SC here is a weird entropy which I've computed in this effective picture, where I have some effective gravity here and some effective conformal field theory with a cutoff. All right, any questions? How sort of the Island formula now arises from this doubly holographic model? Okay, so if there are no questions, then let's just briefly summarize this part. Just to reiterate, right, we have these three different perspectives. This pure CFT perspective, which you should treat as a fundamental description, and this, and then the brain perspective, which is sort of like some semi-classical or effective description of your system. And we had the bulk, which we really just use as a useful tool. And the punchline, sort of, or the thing I wanted to convey here is that the standard RT prescription really gives you, in these doubly holographic settings, gives you the Island formula in your effective theory. And so from this point of view, there's really nothing new or mysterious about it. It just follows from sort of rules and calculations that have been accepted for the last 10, 20 years. Okay. And then there's some other thing that Fatul maybe brought up in the first session, or someone brought up in the first session, namely the question, but why or how do I understand that actually my island is in the entanglement wedge of A? So why does A contain information about my island? And from this higher dimensional perspective, this is extremely clear, right? Because whenever I'm in this phase, from the bulk point of view, my island corresponds to a region which literally is in the entanglement wedge, just by sort of like standard, by usual ADS standards. So just to sort of reiterate, right? So the entanglement wedge is the region in the bulk, which I can reconstruct from access to these regions A, and that's the region which is bounded by the proper RT surface. Okay. Now I've cheated a tiny bit here, namely that what I sort of haven't told you is that in the simple situation I considered so far, this here is just not the dominant phase. And the way you can understand this is just remember that this brane here really has a lot of volume to the left and to the right. So this RT surface is really, really, really large. And if I just cap off the regions, I will always get smaller RT surfaces. However, there are situations which we can also model within these doubly holographic scenarios where we actually see a phase transition and where an RT surface like this will become dominant. Okay. And I'm just going to pause again for a second to take a sip and see if there's any questions sort of about what I said up until now. Okay, so then let's sort of go to the second part of this tutorial, namely, how does this relate to black hole information paradoxes and so on. And Raghu sort of introduced this, but let me maybe just still spend a few more minutes on explaining sort of certain features of some entropy paradoxes or the black hole information paradox, or in particular, a very special version of the black hole information paradox for eternal black holes. So what we have here is, again, space-time where I have a two-sided black hole and some bath region, which is non-gravitational out here. And what I do is I just put the temperature in this non-gravitating region to match the temperature of the radiation that comes from a black hole. So this system is really in thermal equilibrium and doesn't really seem to evolve. Now, I assume that the state here on the t equals 0 slice is just a pure state, which is in the thermophile double. And the important point here, or what that means for us, is that quanta of radiation on both sides of my black hole are entangled in a very particular fashion. So for example, here, I've drawn two green quanta. They're both moving to the right. And here in the radiation region, I have two red quanta, which move to the left. OK. So if I'm now calculating the entropy between my bath region and my gravitational region, so the entropy of this R subsystem here, which covers both baths, then I see that those two red quanta do not contribute, right? They're both in the same region. Well, they're entangled, but they're both in the same region, so they don't add anything to the entropy. And similarly, for these two green quanta here in the gravitational spacetime, they're not part of my radiation region R, and so they also don't contribute to the entropy. However, if I let my system evolve forward in time, then say this light green quantum becomes this dark green quantum, which now is inside the black hole, whereas this light green quantum escapes out in the bath and now lives in the bath. And similarly for the red one, this one will fall into the black hole after some time, whereas this here just stays in my bath region. So if at a later time, I again compute the entanglement entropy between my bath regions and my gravitational region, I'll see that those pairs now do contribute to the entropy. Well, why is this? So for example, this dark green quantum here is entangled with this. And by computing the reduced density matrix, I break this entanglement. And so I get a contribution to my entropy. And similarly for the yellow one. Now, that's a problem. And there's, I guess, one thing you just have to believe me, that this process just goes on and goes on and goes on. And so as I let time run forward, this entanglement just builds up without bound. But there's a problem here, because really my black hole region has a limited amount of entropy, and this only can be entangled so much with a radiation region. So at some point, I get into some entanglement paradox where the entanglement entropy I calculate here is bigger than it can be, just by considering the finite size of my, or the finite number of quantum states in of my gravitational region. And now if I use my Allen formula, this becomes, of course, resolved. And the way it gets resolved is that at some point an island appears, which covers the interior and a bit of the outside of my black hole in this case. And so if I compute my entropy at some later time, it contains both this dark green quantum here in the radiation region and this dark green quantum here in my island region. And because of this minimization procedure, when computing entanglement entropy using the island formula, I can sort of plot the entropy in the island phase like so. It's just a constant line. And in the previous phase where I didn't consider the island, which grows without bound, but I'm just always sort of like following the lower of the two curves. And I find a page curve for an eternal black hole. OK, so how do we see this in the case of these doubly holographic scenarios? Sort of like the simplest model is to consider a massless topological ADS black hole, which is a fancy word for saying ADS Rindler space. So what I do is in the bulk, I sort of consider the two halves, or I consider ADS vacuum. I split into two halves, and I go to coordinates which are natural sort of for an observer, which starts going to the black hole from the boundary and then returns back to the boundary. And the CFT, how does it look like? I have a CFT on a sphere. So this up direction is time. A sphere would just be a cut through this picture along this dotted line here. And one half space contains one CFT. The other half space contains, well, same CFT. But I go to a conformal frame where I map this half sphere or disk to a hyperbolic space. And I will do the same for this half sphere. And I will also map this to a hyperbolic space, so that really the distance between those 2 points here is infinite. OK, so after doing this conformal transformation, or after doing just holography using this setup, I'll find that my CFT is in a thermal state of a very fine-tuned temperature. Now, from the brane perspective, what will I find? The brane cuts this Rindler horizon. And so the Rindler horizon will also be induced on the brane. So the gravitational spacetime again, we'll have a horizon, and my black hole here will radiate and will be in equilibrium with some with radiation of a certain temperature. And then to one side of my brain, I've glued this pink region here, which is, again, a non-gravitational bath region, which also has a finite temperature and has a CFT living on hyperbolic space times time. And similarly on the other side, where I've just colored it blue for clarity. OK, does this make everyone happy?
Sorry, Dominic, in the middle picture, the green vertical line is the brain, and the horizontal pink line is the horizon.
Yeah, that's the horizon. That's right.
And this is a time slice in ADS3. I should think
so
of
this is right. This is the t equal to 0 slice. So this is really the bifurcate horizon. So this dotted, this dashed line here is this point.
Okay.
In this picture.
Oh yeah. Okay. Good. Yeah. And the right picture is just the 2D picture, right? That you would get by deleting the blue bulk stuff in the middle picture.
Exactly. Exactly. So, I guess the point, or one of the points I want to make is that you can really do this in any dimensions. It's just kind of hard to draw like something.
Yeah. And just to make sure, so in the middle picture, there's a point where the blue semicircle and the red semicircle meet. There are two such points, right? And one of these points is like on the right-hand side picture, you imagine the red and the blue triangles to be joined at infinity.
Exactly. So here you see how they're joined at infinity. And here, what's happening? Okay.
Oh, okay. Makes sense. Yeah.
Okay.
Thanks.
Great. Okay. So now the big question is, okay, so we've discussed before that an island should appear after some time, but how do we see this? Well, again, we're going to consider some radiation region R in our bath, and then cheat and go to our bulk prescription and just calculate the entropy using standard RT surfaces. And we see there's two choices of RT surfaces. Again, one where I connect through the brain, but on one side of the horizon, and then this is the dotted one. And then there's the solid candidate RT surface, which connects through the horizon and connects the two different sort of CFTs, so this CFT and this CFT. Now, what we expect sort of from the story I told you before is that we start out in a phase where we have growth of our entropy and no island. So that would mean that we start out in the solid no island phase. And then after some time, there should be a phase transition to this dotted line here where we're in the island phase, which before wasn't really favored because remember, there's lots of volume here. But yeah, this should be dominant at some point. And with a bit of work, you can actually reconstruct the full page curve. I'm not going to discuss this here. I'm just going to sort of try to convince you that this is qualitatively really what you will find. And in order to do this, let's first go to the island phase. So what we see here is that the corresponding RT surface lies, like each of these RT surfaces here, lie to one side of my horizon. And it turns out that time evolution, and Raghu already mentioned this, well, actually, I don't know if he mentioned this, but time evolution of a single side as a symmetry, right? It's like in flat Rindler space, where by time evolution in Rindler coordinates, it's just by boost symmetry. So if I just evolve time forward in one of these half spaces, the area of my RT surface remains unchanged. Now, that might be confusing for reasons, but since I see that time sort of runs short, I'll just come back to this if somebody actually is confused by it and will ask a question. But for now, the point I want you to take away here is that because my RT surfaces are on one side of the horizon and time evolution on one side of the horizon is symmetry, my RT surface will just stay constant, or the area of my RT surface will just be constant. And then secondly, and I already mentioned this, right? Really, you should think of this picture as two copies of this picture. So there's a large extra volume, which is created by the back reaction of the brain. And this RT, the area of the RT surface is really, really big. So the entropy is huge. And so we don't necessarily expect to start in this phase. However, since the area of the RT surface doesn't change, whenever I have another phase, which might start with a smaller entropy, but it grows without bound, I will necessarily end up in this island phase. Now, the other phase we start with is the no island phase, and here our T surfaces cross the horizon. And this one, Raghu mentioned that time evolution on both sides forward of my system are not a symmetry anymore. And so what we find, and this is a calculation which has been done in a slightly different setting by Hartman and Aldacena, is that the entropy calculated by these RT surfaces grows linearly in time. So let me try to draw a little picture to make this maybe intuitive. It's particularly easy in d equal to 2 and d bigger than 2 is more than 2 dimensions. It's very similar. Remember that I mentioned that you need to regulate your RT surface because technically its area is infinite. And so for this particular setting, my cutoff surface looks like this. It's this kind of like bend shape, which you also might recall from Raghu's talk. Now, if I just calculate an RT surface in 2 dimensions, it's just going to be a straight line. This picture here, this is one boundary. So this would be sort of like the region around here on my red system. And here is my blue system. So it would be the region perhaps around here. Now, as time evolves forward, my RT surface goes up and up and up. This diagram also evolves with time. And you see that the cutoff sort of retreats. So if I evaluate the area of my RT surface, it just grows. Another perhaps more physical point of view you can take is that you see that a lot of the RT surface is actually inside the black hole. And that might be familiar to many of you, right? The RT surface has to go through the wormhole, which connects the two sides of my black hole, but this throat just grows with time. And this is really what leads to the growth in entropy here. And in 2 dimensions, it's very similar, except that my RT surfaces start taking this funny shape and start bending down. But qualitatively, that's the same story. OK, so yeah.
Can I ask you a question? So in this picture, I'm a bit confused about, because it seems like in the upper circle you have drawn the minimum surface that connecting the blue region and the red region, which corresponds to the lower picture. But somehow I don't see that in the upper picture, the minimum surface will touch the green region, which is the brain. And in the lower picture, indeed, you see that your minimal surface, when connecting red and blue region on the 2 boundaries, they go across the green region, which I think corresponds to the brain. So
right. Yeah, how you should maybe imagine this picture is sort of a projection into this direction. So you look onto this thing here from the side. So this is really sort of the bulk perspective still. It's just I've sort of kept the brain here. And I show you the brain. And this is just how the RT surface spans through the bulk, like so.
Yeah, maybe I could ask you later.
OK, sure, yeah. OK, then since I think I'm out of time, let me just maybe add one small comment. Well, first of all, you can do little plots here in higher dimensions. That's great. But I think the really nice part about all of this is that the page curve in these doubly holographic settings very obviously follows from something very simple, namely sub-additivity. Right? We have 2 potential candidate surfaces. And sub-additivity tells us if we consider 2 regions A, so here, this A would contain my gravitational region and a bit of my bath, and B, which contains the same thing in the other CFT. Then its overall entropy must be bounded from above by the entropy of SA and SB. And if you just look at what RT surfaces this corresponds to, it's really that SA plus SB are RT surfaces which cut through the brain, so are in the island phase. And SA union B are the ones which connect to the horizon, so the thing that grows. And so we know that this stuff grows, but at some point, just by sort of standard sub-additivity, it must be bounded from above by something that is constant. Okay, you can do the same thing also for extremal zero temperature black holes. And I think the only interesting point to mention here is that unlike in the two-dimensional scenario, you actually will not find islands in higher dimensions. That's not really a problem. There's no entanglement paradox here, but it's maybe noteworthy because going to higher dimensions will sometimes give you qualitatively different things. Okay, so to wrap it up, I've introduced these doubly holographic models, and they're great for a number of reasons, but mostly I sort of hope that people will have, or this has given people some intuition and has hopefully made some explanations easier, in particular, how you have to interpret this island formula. Okay, yeah, let's stop here.
Great, thanks, Dominik. We have time for questions. Do people want to just go ahead and ask any questions they have for the next while?
Yeah, I have a quick question. So, okay, so in the D equals 2 case in Raghu's paper, in the extremal black hole, that's when you get an island outside of the horizon.
That's right.
And you're saying that you just don't get islands at all.
That's it,
So,
yeah,
so is there like so are those both the same reasons?
I mean, you can just do the calculation in this doubly holographic scenario in d dimensions, and you will see this. The technical reason is that in 2 dimensions, you have this connected phase here. So, right, so imagine this is your bath, this is your brain, and this is your bulk RT surface, which now connects through the bulk, right? So you have this island phase, and that competes with a phase where my RT surface just falls down into the Poincare horizon. Now, in 2 dimensions, it just turns out that this integral here is IR divergent. So this will always be bigger than this. And so this wins. In higher dimensions, the integral of the area of this RT surface is, well, up to divergence is close to the boundary, is finite. And so they can compete. And it turns out that if you push your brain far enough to the boundary, that the situation will always win.
Okay, thank you.
Hey, Dominik, thanks
Hey.
for the great talk. So, can you make any comment about like non-holographic derivation of the island formula using replica trick, and whether there is any sense in comparing these 2 derivations? Like, are there any limitations in which is an advantage in the other, or is there any sense in comparing these 2?
Right. So, okay, so I had this sort of last slide where I just wanted to show these replica wormhole geometries real quick. So generally, I mean, I don't have to say much about the actual derivation. And again, I pointed out this review of June, which you can find on the archive. And I think that's if you sort of interested in the route via replica wormholes, that's a very great place to start. And then also the original papers. Now, as it comes to comparing those 2, so at least as far as I'm aware, and please somebody correct me if I'm wrong here, is that the replica wormhole calculation or proof of the island formula has really only been done in 2 dimensions. And so the obvious benefit of going to these doubly holographic scenarios is that you can say something about higher dimensions. On the other side, though, these doubly holographic scenarios are obviously more constrained because you're assuming a holographic CFT, which you don't necessarily have to do in the replica wormhole computations. There's maybe, and that's a bit more maybe speculative, but I think interesting to think about. There's always this question, you know, when and how and why should I actually incorporate these saddle points, and when shouldn't I, perhaps? So to give you an example, if in JT gravity I compute the partition function of a system which just has 2 disconnected boundaries, you know, I might want to consider contributions to my path integral which connect those 2 boundaries, and that leads to non-factorization. So the product of 2 partition functions will not really be the product of the 2 partition functions, if if you understand what I mean by that.
Yeah, yeah.
But in higher dimensions, again, right, like we expect n equals to 4 super Yang-Mills theory. That's just like it's a nice theory. And the partition function is just a number. So that should clearly factorize. And I think what's kind of interesting to take these doubly holographic systems and, where it's very clear what the distinction is between this brane perspective and boundary perspective, between your sort of approximate and fundamental description of your system, and understand sort of how wormholes arise in this description.
I see. Okay, thank you.
Well, maybe I can just add a quick comment. Like one way to think about these replica wormholes is that they're sort of the derivation of the island root. So just like Liukowitz-Maldacena gave a derivation of the Ryuta-Yanagi formula, right? Using some boundary replica trick, fill in the bulk using some saddle points. So you do exactly the same thing. Like you set up the replica trick on the boundary, but in the bulk, you just do the path integral over geometries. And then you find that there can be such saddle points. And yeah, they've only been done in 2 dimensions. In high dimensions, people believe they still exist and so on, but the explicit computations have not been done. So I would say that the relation of the island to the replica wormhole is just like RT to the Liukowitz-Maldacena derivation. Like what are the saddle points that contribute at integer or any index?
If you include if you include wormholes between the boundaries and you get this non-factorization, why is that an issue?
Well, usually we hope that the partition function is just a number, and numbers should factorize. I think that's sort of the short answer.
Because you're computing
one comment on.
Yeah, Raghu.
So I was just saying, so there's the ZZ star computation, but this is little different, right? Because in these red things that Dominik drew, the cuts that are in the region in the radiation are already connecting the pink sheets, right? Like the cuts sew up the end sheets. When you set up the boundary replica trick, the manifold, so even though these connections are not drawn here, these pink sheets are connected in this picture. So then it's not much of a surprise that, okay, you can allow these green things and it's okay. The spectral form factor is a different case where there is not even a coupling between the red boundaries. You see, there is some branch cut right here that
I can't really draw something on here, but
so here it's already connected, the red region.
Yeah, I mean, even the spectral form factor is there you, at least if you calculate the average version, then, well, you average over something, so you introduce some correlation perhaps between your partition functions. So you might also there, you won't necessarily be surprised if there's some additional contributions which destroy factorization. But yeah, I mean, if you just compute something like a partition function of a system which consists of like 2 completely disconnected boundaries, that's kind of odd. Like you would expect that both boundary gives you like a fully well-defined system, their partition function are numbers, and you could just multiply them and you get the right result.
So I have a question. So the black holes you considered, they were 0 mass black holes, right?
That's right.
So what would be different if you considered non-zero mass?
I guess the calculation would be much harder. So the nice thing about, well, the existence really of these types of models is that the calculation, because really the geometry in your bulk is just vacuum ADS, is very simple, right? You have all the symmetries of vacuum ADS you can now exploit. If you change your mass, that will become more difficult. But that being said, overall, again, I would expect, and I think a similar question was also asked this morning, the qualitative story will still be the same.
Okay. So it seems like this story seems to rely heavily on the just changing coordinates to these Rindler-like coordinates.
That's right, yeah.
Okay. So it probably wouldn't work for like spherical topology black holes.
Well, I mean, you can set up the calculation. The beauty of like this particular one is that so in order to obtain those plots of the page curve, you can go analytically very, very far, and the only thing you have to do at the end is like numerically solve like an ODE or two. If you can certainly set this up in more complicated situations, but probably you won't, well, or most likely you won't be able to go that far analytically. So the numerics are going to be much heavier. And I mean, Raghu has had a paper also on this. So maybe if you want to add some more things about numerics in more complicated cases.
Well, with George Santos, who did most of the heavy lifting with the numerics, you can put you can consider like a planar black hole. So we didn't do the spherical topology case just because the numerics are harder. But if you take a planar ADS Schwarzschild, the picture is pretty much the same, what Dominik described. Early times, you have this surface that enters the horizon in this highest dimensional description, grows linearly in time, a la Hartmann-Maldacena, but then at late times, it stays outside and it's time independent. There's an island at late times.
Okay, thank you.
So maybe I can ask a question. In the zero temperature island that you said that is not there, if you modified the action on the brain to include some more terms rather than just the tension,
right?
Could you break that, or could you change the place where the island appears or disappears?
Yeah. So I haven't talked about this, but in general, you can. So in 2 dimensions, in fact, if you want to reproduce the JT calculation, you have to, because the gravity that gets induced on the brain is not JT gravity. So you got to add JT gravity by hand. Now, the issue, though, is that if you want to make island formation easier, you essentially have to add a counter term to the brain. So something that that makes your gravitational coupling stronger. And in practice, that means you're adding a term which is like Einstein-Hilbert term with the wrong sign. And
there's a bare term in the action on the brain, which is the intrinsic Ricci scalar on the brain, and with the minus sign or something.
Yes, that's right. And you in order to like at least compensate it to some extent, and there's essentially 2 problems there. One is that the counter term you have to add just like grows extremely fast, and second, if you just add a counter term which is too negative, then your system will presumably just be unstable or nonsensical. In fact, you could have also, like when I said here that this will never be the dominant phase, that's also not quite true, right? You could imagine adding some sort of negative Einstein-Hilbert action onto that brain, and then it will become dominant. But we kind of believe that these theories don't make much sense.
I see.
Generally, you have a negative tension brain if you do that.
Yeah. Okay.
Okay, thanks. Are there any more questions? Okay, great. So I posted the address for the virtual coffee chat. People are welcome to meet in there afterwards. And just thanks to Raghu and Dominik for some great tutorials, and hopefully we'll now fully understand the talks on Monday. And thanks to everyone. I was amazed at how 200 people can be so well behaved and coordinate questions so well. So thanks to everyone for the questions and for participating. And I encourage everyone to unmute and thank Dominik and Raghu for some great tutorials. Thanks.
Thanks, Jonathan, for organizing. Thanks a lot.
Thank you.
Thanks. Okay.
Okay.